Good morning, everyone. Just testing the slides here. Yep. So first of all, thanks for the invitation. Pleasure to be here. So today I'm going to talk about this project, which is the project that I've been working for my PhD thesis since I got here, since I started at Iowa State University with Dr. Daniel Linhares, my advisor. And as part of this session, this conference, we focus specifically in this project on trying to understand, use this farm collected in production systems. How can we collect that data and get insights, understand what are the drivers of, in this case, the wing to finish mortality? That's our question. So that's the approach that we're going to use, that I'm going to talk about today in this presentation. That is the whole herd approach, which basically consists of collecting and integrating diverse and dispersed data that is already available in the production systems nowadays. But unfortunately, most of the times they are disconnected. So that's kind of similar to what people do for example, weather forecasts. So if you want to predict the weather, if it's going to rain or not, you're not going to use only one data, only temperature or humidity. So you use a lot of data, different data to answer that question. And that's what we're going to try to do today. That's what we have been working to focus on, the question, which is the wing to finish mortality. And the good news is that we already have that data available in most of the swine production systems. And specifically for productivity and health, that's the most available one. And from that, we can get these data-driven decisions, support that. We don't have to go into details into that, but just to remind you guys, from breeding to market, the production process, we have many phases of production. And most of the times, those phases, they are separate. We're going to have mixing pigs, commingling, different sources. And throughout each of those phases, we're going to collect productivity data, but also health information, infrastructure, diagnostic information, environmental information. So many different data streams across many different phases that are not connected. And that's our challenge, our goal here in this project, to integrate that data to do this whole herd approach. And our analysis, our unit of analysis in this case is the closeout. So just one example, imagine this closeout, one group that received pigs from 2 different nurseries, one of the nurseries from 2 sow farms in different weeks, and the other nursery, a single sow farm. So that happens very often in many production systems. So how to track and create like a background check for this finisher group in terms of what happens since breeding to market. So that's what we did. And most important is to do that on an automated way. So we develop algorithms that once we spend a couple of months developing it, but once it's done, just a simple 2-3 minutes running the statistical process, statistical software, it's going to integrate that data automatically. And once we have this final model, which we call the master table, then we can apply the whole herd approach that I mentioned in the first slide to investigate the wing to finish mortality. So for this analysis, we worked with around 2,500 closeouts from 2 different production systems in different time frames, but similar. But pretty much the data that we use, that we collect from those systems, were breeding to wean sow farm productivity, the information productivity, the health status, diagnostic information here for PCR detection, and also tissue submission, the DxCode, facility information, environment information, and also the closeout data by itself for the nursery and finisher phase, and the true wing to finish groups. And okay, what we do once we have that data, right? So that's when I said that we apply the whole herd approach to investigate the wing to finish mortality. And in summary, once we start analyzing this whole herd data, or this master table from those production systems, for wing to finish mortality, the major component is that sow farm productivity and health, they are highly associated with the downstream performance of the groups. Okay, we kind of expected that, but if you don't have the data, if you don't have the model, you're not going to put the numbers, you're not going to put the delta, the difference. And here's just a quick example. So in the y-axis for those graphs, we're going to have the wing to finish mortality, and in the bottom, we're going to have some of the variables. So for example, here we can see that on the far right, top right, we're going to see that sow mortality in the sow farm, the annual projected mortality of sows, the groups that were weaned, and the mortality for those groups, the sow mortality, was higher than, within this high quartile of 16%, they also had a higher win-to-finish mortality downstream. And pretty much the same thing for the other components related to productivity. So the better the total born, associated with better win-to-finish mortality, fairing rate, higher pre-weaning mortality, higher downstream win-to-finish mortality for those groups as well. Like I said, productivity and health. So in this case, health, how we're going to measure that? PRRS status is what pretty much all the production systems they collect. So what's the association of PRRS status in the sow farm with the downstream performance? And here we have two different classifications that the production systems use, but they are saying the pretty much the same thing, which is PRRS unstable groups with a high prevalence in the sow farm. So we have the unstable in the left category, and the category 1A, that will be similar to the new ASV category proposed this year by Dr. Holtkamp and co-authors. And this category 1A will basically represent the first 16 weeks after an outbreak in the sow farm. So we can see this higher win-to-finish mortality from pigs weaned from those groups as well. And we can also analyze and do some interaction between some factors. So for example, here we have, on the purple box, we have different weaning age quartiles, but we can see this trend that across all the weaning ages, the major component were the groups that within each weaning age weaned with status 2, which is the epidemic status for PRRS. So weaning age is important, but here we can see that the one that is playing the major role in this case is the PRRS status. So it's important also to analyze the interactions behind the numbers. And one of the things moving forward for the post-weaning phase, we integrated data from PCR detection for PRRS and the diagnostic code, which is basically from the weaning to finish. Every time that a veterinarian or people send tissue to the VDL, the diagnostic, that material when arrives at the VDL, the diagnosticians will assign what were the pathogens identified. And from across all the phases, from weaning to finish, we collect all the data for each group. And one simple analysis that we did was just basically comparing the groups that had any tissue submitted to the VDL at any point of time, which is the DxCode positive, and no DxCode, we have groups that never had any tissue submitted to the VDL. And just by sending here, we can see this trend that increases win-to-finish mortality. And Dr. Rademacher, he mentioned, showed a few of this information yesterday, but why I'm showing today to you guys is because there's a component behind those analyses that we have to understand, which is also the title of this presentation, which is the causal inference. So talking about causality, if we're going to interpret these as a causality, we're going to see that within those groups that had tissue submitted to the VDL, if we compare groups with influenza that were influenza positive compared to groups that were influenza negative but positive for other pathogens, we can see that influenza here have a higher win-to-finish mortality compared to those groups, and also compared to groups that never had any tissue, the 8% one. So the interpretation will be that influenza being detected in the tissue in the post-weaning phase is associated with a higher win-to-finish mortality, correct? But once we break that down by PRRS, we see here that PRRS is the major co-founder, right? So if we see the PRRS negative groups and flu positive, so only PRRS only flu without PRRS, we can see there's a big difference when we have flu and PRRS. So that result that we saw in the previous slide is due to pretty much the interaction between PRRS positive and flu positive. So it's important, and that's important when we are analyzing this data from the production systems to think about those interactions running in the background, right? And especially focus on that topic, what we're going to do is the causal inference analysis. So how can we answer a question like we saw the influenza question? How can we answer a question using causal models? Usually what we do is an experimental study, right, where we control for all those factors running in the background in the co-founders. But can we use that with observational data that is collected in our routine? And the answer is yes, and for that we are using this called the propensity score. But basically here the example is the question is what is the impact of PRRS in the nursery mortality specifically? And PRRS here is the first 16 weeks after the outbreak. So what is the impact of that? So if we look, will be that line, the green line in the middle between the stocking weight and pre-weaning mortality, will be the direct effect, but we have the co-founders acting in the background, which will be parity and season, and also what we call the mediators or other factors associated. So once we are going to analyze this whole database, there are models that we can control for that. But let's just give an example. Let's see the impact of PRRS on nursery without controlling for anything, just using a simple univariate analysis. What will be our delta? Or this will be similar to what we do with pivot table in the routine. We're going to see that PRRS epidemic groups have an increase of 2.26% win to finish nursery mortality. So using that model that I mentioned to you guys, where this is the most important thing. First, once you build the question, you have the question, you have to do this DAG, or this graphical visualization, to understand what are the factors involved and control that. And there are models, statistical models for controlling that. And using those models, we use specifically in this case the inverse probability weighting. We control for those factors, and it's kind of gonna weight the confounders. And actually, the same data, we're gonna see a difference now of 5.38%. So important to, we have the opportunity to do causal inference from observational data once we have that data. So the more data that we collect, the more availability we have and the more confidence we have. And we saw the identification of risk factors, we saw in causal inference analysis, but also prediction is possible. And especially because we saw that self-farm variables, they are really important to the downstream performance. We built a model, a multiple regression model, that accounted with 14 variables from the self-farm only. And that model, it's going to estimate, we can see in the x-axis, estimate the win to finish mortality of the groups based on the variables from the self-farm, and it's going to compare. Each circle will be a closeout there. And we saw that those 14 variables, they had a correlation of 80.91% with the downstream win to finish mortality. So a good portion of the variability of win to finish mortality being explained by self-farm related factors. So also, again, confirming the importance of this phase, the pre-winning phase to the post-winning phase. And this is the same thing, the same data using the model, but I broke down for a few of the variables that are included in the model. And if we look at the column of actual mortality, we're going to see that we have the actual mortality, the groups that had mortality more than 10% of win to finish mortality. And we can see that for higher SAL death rate, for the higher pre-winning mortality, for the epidemic PRRS status, pretty much most of the groups were within the 10% of win to finish mortality. And the model, the right column, which is the same thing, but with the predicted mortality by the model. So when they had like an epidemic PRRS status, we can see that the model predicted 47% of win to finish mortality. So not exactly the same, but following the same trend, similar. And this is the same information from that model, the 14 self-farm variables model, but plotted by a weekly average. So comparing the average win to finish mortality, the actual mortality for the weeks, compared to the predicted mortality by the model. And it's a little bit underestimating, right? It's not overestimating, but we can see that those variables, they are good predictors of what's going to happen in the downstream performance. They are good information to understand what's going to happen. So as a final take homes here in the discussion, the first thing that it's the most important, in my opinion, is that it's important to have this automated model to consolidate multiple data streams. The data change over time within production system and between production systems, so you have to have algorithms specific for that. And once you are able to integrate the data, then you can apply this whole herd approach, which will be, for example, what we saw, the risk factor analysis or causal inference analysis, and also forecasting analysis. And like I said, important to understand that this is very time specific and place specific, will change over time within production system, so it has to be updated constantly. And the final message will be that self-farm health and productivity, good proxy of downstream performance. In my opinion, what that means is that the quality of the weaned group, that's a really good, really important thing once we're gonna think about the nursery mortality or the finisher mortality. So really important to think about that when you think about the post-weaning mortality is to really do a good job and have good quality of weaned pigs downstream. And with that, just say thanks to my team, the field epi team at Iowa State, and a special thanks to my advisor, Dr. Daniel Linhares. And I'm open to any questions. And a special thanks to IoSelect Farms and the handler folks, especially to Dr. Pete Thomas, Dr. Tara Donovan, and Dr. David Brozero for all the help and partnership throughout this project. Thank you.